All right, welcome back to Biostats. We have a couple more probability rules to cover. We're going to do that in this video, and then we'll be practicing all of this in the in-class exercises. All right, so the rules we're going to discuss in this video are Bayes' theorem and what's called the law of total probability. So Bayes' theorem states that if you're interested in knowing the conditional probability of some event, like what's the probability that event A occurs given that B is known to occur, how would you calculate that from other things that you might know? We can use it with this fraction where the numerator is just the probability that A happens multiplied by the probability that B happens given that A has happened. And then the denominator is the probability that B has occurred. It's really just a general multiplication rule followed by some algebra. So if you remember the general multiplication rule, it was the probability of getting A and B. You could express that in a couple ways that depended on some unconditional probability, the probability of A, multiplied times the probability that B happens once you know that A has happened. Or you could do it the other way around. What's the probability of B and the probability you get A given that you have B? So if we look at that general rule, multiplication rule that we saw in the previous video, and we just divide every side there by the probability of B, what comes out is this form here of what's shown above, which is to say Bayes' theorem. So it's back from the good old days of statistics when you could have a whole theorem and law named after you for just doing some basic algebra. And note also it may be helpful for you to think of the probability of A given B in this other form over here is just it's the joint probability of A and B divided by the probability of B. That's equivalent because this numerator can be expressed in this way. So you'll sometimes see Bayes' formula written in either of those two forms. It's a very useful rule for solving probability problems in situations where a lot of our information comes in the form of conditional probabilities like this, but we want to turn them around and express a new conditional probability. It's often used in conjunction with the law of total probability. The law of total probability looks like one of our previous rules because it talks about some events, some event I sub 1 going all the way up to k. So event sub 1 versus up to event k, that's got to cover the entire sample space, and they've got to be mutually exclusive events. So we saw something like this before in Rule 2, and what we just said is if those conditions occur, if we sum those probabilities, we always get 1. The law of total probability says if you sum up those probabilities multiplied by the probability of A given that event, then you get the total probability of A. So if you have a bunch of conditional probabilities of event A, you don't know what the probability of A is without any conditions, but you do have a whole bunch of auxiliary events and you've got some information about those, then you can calculate the probability of A by summing up over all the possible values of some auxiliary event. And this is a really common way to get the denominator in Bayes' theorem. All right, so let's work through an example and hopefully see how this is frequently applied and how you can use these two together. So this is a really common type of example that shows up a lot in medical testing, and doctors need to be aware of sort of how to do these calculations. So a disease is found in 8% of the population. There's a diagnostic test for the disease. The test has a false positive rate of 10%. So it's a false positive rate. So it's a positive rate for testing positive on the disease, but it's false because what that means is that these are healthy people, at least healthy with respect to this disease we're talking about, and they still have a positive test. So that's the sense in which it's a false positive. Okay. And then it's got a false negative rate of 5%. Someone with the disease will have a negative result 5% of the time. So this is almost always the case that our diagnostic tests are not perfect. They have a false positive rate and a false negative rate. And what a doctor wants to know is if they have someone in their clinic who has a positive test, what's the chance or what's the probability that that patient has the actual disease, right? They've tested positive, but that doesn't necessarily mean that they have the disease. So let's think about how to break this down. And remember, the general recipe for solving a probability problem is to try to express in notation all of the facts that are given to us in the problem, and also what it is we're trying to calculate or we're being asked to calculate I'll put all that in notational form, in some clear notational form. So the first bit, I've highlighted it in blue. The disease is found in 8% of the population. I'm going to use disease status equals Y for yes or N for no. And so that's a statement about the disease in the full population, right? So it's not conditional on anything. It's just the probability of the disease being yes is 0.08. All right, what's the next bit of information from the problem? I put it in green here. Hopefully this shows up okay on the screen. 10% of healthy people will have a positive test. So that, notice, is a conditional probability, right? It's not talking about the entire population of people. It's only talking about people that are healthy with respect to this disease. So given that their disease status is no, the probability that they test positive is 0.1 or 10%, right? So it's important to note that this 10% is a conditional probability, because it's only talking about a subset of the full population. It's making a statement conditional on the fact we're talking about healthy people. All right, and the next bit of information is similar. It's someone with the disease will have a negative result 5% of the time. So with the disease status is yes, but a negative test, and that's going to happen at 0.05 or 5%. So those are the three probability statements that are given to us. What are being asked to calculate? We're being asked to calculate if someone tests positive, so given that they have a positive test, what's the probability that they actually have the disease, right? And that's what we don't know. If you look through these probability statements, you'll see that we don't have that stated in any of them, right? So this is something we're going to have to calculate. You might want to pause the video and think about how you might calculate that. And I'm going to move ahead here. As you would expect, given that this is a lecture on Bayes' theorem, we're going to use Bayes' rule to do this. And so if we just think about those events, this was previously written as the probability of A given B, and Bayes' theorem was expressed in terms of A and B, but now we're just going to go back to our definition, and everywhere we saw A, we're going to say the event A is disease equals yes. So here we have the probability of A, which is the probability of disease equals yes, multiplied by the probability of a positive test given A. And so our B condition is the test is positive, and so that goes in wherever B went in the formula, the probability of B given A. And our new notation is the probability of a positive test given that you have the disease. And we divide through by the total probability of having a positive test. All right, so that's how we would apply Bayes' formula to this. We have some of these pieces that we need in order to solve, but not all of them. So let's walk through how we might go about continuing to solve this problem here on the next page. So I've taken out the problem and just put the axioms that the probability statements we were given up here, and how we were going to try to attack it with Bayes' formula. Because if you express things, I should have emphasized this, I'm going to back up to the previous slide. If you express things as this conditional probability and you look through your probability rules that were given to you and are on Canvas in the outline for this module, you'll see that Bayes' theorem is the one that tells you how to calculate a conditional probability. So that's the one that should sort of leap to the forefront, because that's the one that sort of matches what we're trying to calculate here. How do you calculate conditional probability? Well, Bayes' theorem will tell you how to do that. Okay, so that's the Bayes' theorem with the substitution with respect to the events that we're talking about here. Let's think about what we have and what we don't have. Well, up here in the numerator, we've got the disease equals yes, and we've already extracted that from the problem. So we're just going to substitute in 0.08 for that. All right, what about the next bit? We've made some progress, but we still don't need to replace some things with numbers. What's the probability of a positive test given that you have the disease? We don't have that exactly. We do have a probability of a negative test given that you have the disease. And so if you think about it, there's only two options for your test. It could be positive or negative. We're not considering an ambiguous test result here. So we can use the complement rule. What's the complement of this probability? Remember that in a conditional probability, this is the random event and this is the known event. So the complement is the other option in the sample space, not negative. That means a positive. And so we know that this is 0.05. That means the complement of that is 1 minus the probability of what we had there. So 1 minus 0.05 and gives us a probability of 0.95. All right, so now we're going to be able to put that in here in the numerator of Bayes' formula. So we're making some progress here. we have this thing that we don't know. The denominator is what's the probability of a positive test. So this is not conditional on anything. If you just reach into the population at large and grab someone and test them, with their permission, of course, what's the probability that you would get a positive test? So we don't have that exactly. We have some statements, some conditional probabilities about testing, but we don't have the unconditional probability. And I gave you a hint already saying that we often use this to calculate the denominator Bayes formula. We can use the law of total probability here. So the law of total probability says if we want to know what's the probability of a positive test, and we've got a bunch of conditional statements about the probability of a positive test given some extra event, in this case it's the disease status, then we can sum them up and weight them by the probability of that disease status. So in our situation, there's only two disease statuses, disease yes and no. And so this summation just expands to the probability that you have the disease plus the multiplied by the probability of testing positive given you have the disease, and you add that to the probability you don't have the disease and your probability of testing positive despite the fact that you don't have the disease. So it's your true positive test here and your false positives down here. And so if you do that, 8% of the population has the disease, 95% of those tests will be positive. 92% of the population, that's the complement here. I didn't do that explicitly, but hopefully you can see that the probability of disease no is the complement of 8%. So that's the 92%, and there's a 10% false positive rate. So if you multiply those together and add them up, you get the total probability of a positive test, 0.168, or almost 17%. So now we can substitute this in the denominator. We're not going to round off the probability. We won't round it off to 0.17. We'll just keep it at 0.168. And that allows us to now solve for the probability of having the disease given you have a positive test. And in the end, it's about 45%, 0.452 in proportion notation. Notice that the test looks pretty good. 95% of the time it works if you've got the disease. It only fails 10% of the time if you don't have the disease. So it sounds like it's really impressive, but still, just if your only evidence is a positive test, there's less than a 50% chance that you have the disease. And why is that? It's because the disease is relatively rare. So most people don't have the disease, so you're going to have a fair number of false positives because 92% of the population is negative for the disease. So this is just the summary of that. The question again, highlighted in red what we were trying to calculate, and that's what we just calculated. This is information that a physician can use that, even though we have the test as coming up positive, we still know there's a pretty good chance that they don't have the disease. And so we might do a follow-up test or just treat it as a conditional diagnosis. And so that's a very useful way to rearrange probabilities, and you'll see this a lot in the medical literature. There's another way to think about these Bayesian problems that helps some folks. So I'm going to walk through this in a graphical manner, the same probability statements, the same problem, just going to sort of visualize these different pieces, and hopefully that'll help folks if seeing the notation and the algebra is not as intuitive for you. So one way, if you're dealing with the probability of a couple of different event systems, one way that you can display them often is with this box where you can think about going from 0 to 1 for two different axes, and we can put the test result. We'll have a positive test down here and a negative test up at the top, and the disease status is yes. Excuse me, I should have put yes, not disease, and no on this axis. And so, 1 times 1 for the dimensions of the square is a probability of 1. So we can sort of draw rectangles here and use the areas of those rectangles as measurements of the probability. And so this is a handy trick that works in some cases with conditional probability. Okay, so here's the first bit of data that we have extracted, that the probability of having the disease is 8% or 0.08. So this is our axis. The x-axis is going to be the axis for the disease status. So we've filled in 8% of that, and 92% is not filled in. So we can visualize that probability. All right, the next bit of information we extracted from the problem, that the probability of having a false positive was 10%, and that was, of the healthy people, so only this 92% of the square. we go up 10% on the disease testing positive, despite the fact that they're healthy, so negative up here. So it's 10% of that area, but we don't color all the way across, to the full end of the square over here, because it's not talking about of the entire population. It's conditional on them being the healthy population. So that's why the green ends here. So it's just talking about the healthy population. And we can sort of visualize this area here. That's the joint probability of testing positive while being negative in the disease status. And it's the area of that rectangle, or 0.092. This is not something that we saw explicitly calculated before, but it showed up kind of behind the scenes in some of our calculations. All right, the third piece of information we extracted from the problem was this conditional probability that if you're in the disease status yes, then 95% of those folks test positive. It was given to us in terms of the false negative rate. So there's the negative rate, and this is the positive. The false negative rate was 5%, so the positive rate was 0.95. And once again, it's a conditional probability, so we're only sort of shading in a new color the area for the diseased folks. So this 8% of the population, and 95% of them. And so the gray box has an area of 0.076. All right, and so those are the kind of joint probabilities visualized as areas of those rectangles. And the ones we're interested in are only those people that test positive. So we can sort of imagine throwing away the rest of the sample space because we're interested in the conditional probability. What's the probability of having the disease given you have a positive test? So we're going to ignore these folks up here and these folks up here who test negative. And so we can sort of throw away those blocks. This is our new entire sample space, just the sample space of people that test positive. And we're interested in what's the probability that they actually have the disease. So what fraction of this area is in the gray box, 0.076, divided by the total area, which is the sum of 0.092 and 0.076. So this is the denominator that we had before. That's the fraction of the original sample space that is testing positive, so almost 17%. That's going to be the denominator for Bayes' formula. So we get the same answer, but it may help you to sort of sketch these things out and realize, okay, what's happening when we're asking for this conditional probability, conditional on the positive test, is we're just focusing in on a subset of the events of the full sample space. And so that becomes our entire universe of events, and it's what fraction of them are disease yes versus disease no. Okay, so hopefully that helps some folks think about what's going on here. All right, so this has just been a brief video going over these last two rules of probability on our probability sheet. Bayes' theorem, how to calculate a conditional probability of an event given some other information, and the law of total probability, which is how we often calculate the denominator of Bayes' theorem. We want to know the probability of A, but we just have a bunch of statements about the conditional probability of A. And then we can sum them up as long as these other events cover the entire sample space, and each of these events, E sub I, are mutually exclusive of the other ones. Okay, so that's the last of the probability rules. We're going to be working through practice in the labs, but also in the online worksheets that we do in class, the in-class worksheets. And I have one more video on the probability section talking about Bayesian probability a little bit and a perspective that it gives us on the confidence interval. So that's 5D. All right.